So that's pretty much what a recursion sequence is all about. Hopefully not too bad. What the cool thing about is something called summation notation. That's the heart of a sequence and portions like that. Okay, so let's see if you guys remember or notice the symbol here. It's fancy E. So this is the summation notation. So in mathematics, it means sum of things. In this case, sum of numbers. Okay. So how this is going to work out in the summation notation is we're going to have three boxes. Okay. So when it comes to the summation notation, is essentially what we want to do is we're going to adding stuff up. So let's say, for example, let's go back to this example here. Let's say we want to, instead of find the first five terms, we want to add all of the first five terms, meaning we first have to find them, and then we're just going to add them up. Okay, so, but in mathematics, that takes too long to do. So this is exactly what we're going to be doing here, is we're going to just give you this portion and tell you the exact same thing to do. Okay, so when it comes to that, this first box here is going to be the actual function itself, so the sequence. Down here is going to be the start, so where we're actually starting from, and here's where we're actually ending at itself. Okay, and that tells you what sequence you're actually, or what term you're stopping at. So here's an example. Let's suppose we have a sub n is equal to, I don't know, 4n plus 1, for instance. Okay, and if we want to convert this into summation notation, okay, so we're going to do this sum, that fancy E. We're going to put parentheses, just the sequence itself, no a sub n, so it'll be 4n plus 1. Okay, and then we're going to put in n is starting at 1 and where we're ending at. So if it doesn't have an ending stop, we just say to infinity, or capital N itself. Just goes on for forever. Okay. So let's try this here. So write the sequence using summation notation. Okay, so it doesn't tell us where to stop at, right? We're just going to do the exact same thing we did up here. So we have the sum, where n is equal to 1, and we have the function itself, so 3n squared minus 4n. Oh, actually, for instance, if it doesn't go anywhere, we'll go to infinity. How about that? We'll just go to infinity, since it doesn't have a stopping point. Okay. All right, let's keep going. So next one, do the sum of the sequence, minus 3n plus negative 1 to the n power. Okay. Again, at n equals 1, and it goes to infinity. Okay, so now what they did is they did it for us. Now we want to find the sum. Okay, so remember, it's very similar to what we just did here. All we're going to do is find the first couple terms and then add them together. So here, let's go back here. It says we're starting from 1, and we're ending at the 6th term. So what we're going to do is we're going to find the 6 terms first. So 6 terms, right? K equals 1, 2, 3, 4, 5, and 6. 6 terms. Hence we stop at 6, right? So when k equals 1, which is plug into the function, that's k, so 1 squared is 1, minus 3 is negative 2. And we're summing, so plus, that's the first term. Second term, when k equals 2. 2 squared is 4, minus 3 is 1, plus the third term, so this is the first. So this is kind of like a sub 1, a sub 2, a sub 3, a sub 4, a sub 5, and a sub 6. That's basically what we're looking for. We're just going to add all of the sequence up itself, right? So a sub 3 is, plug in 3, that's 9 minus 3 is 6. Plug in 4, that's 16 minus 3 is 13. 5 is 25 minus 3 is 22. And then finally, 36 minus 3 is 33. And now all we're going to do is add them all up, right? Since we want the sum of them. So we just use a calculator. Minus 2 plus 1 plus 6 plus 13 plus 22 plus 33 gives us a grand total of roughly 73. So the sum of this sequence of the first 6 terms, right, starting from 1 ending at 6, is 73. Okay. So let's try B now. Same process, right? Again, we want the first 6 terms. So again, this tells me where I stop at, right? When it comes to, if I said 4, I would stop at 4 terms, etc. So again, plug in k equals 1, that's 2 minus 9 is negative 7. Plug in 2, that's 4. 4 minus 9 is negative 5. Plug in 3, that's 6 minus 3 minus 9 is negative 3. Plus 4, that's 8. Minus 9 is negative 1. So 1, 2, 3, 4, 5. That's 10. That's 1. And then 6, that's 12. Minus 9 is 3. And again, now we just add them. So it could be a negative sum, right? So negative 7 minus 5 minus 3 minus 1 plus 3 gives us negative 14. Okay. So that's how we find the sum stuff. Now, unfortunately, sometimes finding sum stuff could be very, very hard. For instance, what if instead of 6, I asked you to go to 100? Now, you may look at me like, really? I have to find 100 terms and then add them all up? It's kind of ridiculous, right, when it comes to it. So when it comes to things like this where we can't actually, it's technically possible, it's just tedious to do it. In that case, we actually have rules and some properties based off that. So our summation properties, okay? And these summation properties come into handy dramatically when it comes to summing stuff. So it says let a sub k and b sub k be sequences and c be a non-negative number. So just, a number itself. So if c is a constant, like 5, for instance, I can literally pop that out in front. And meaning take the sum first and then multiply it by c. Okay. An example of that would be something like this. Like that. Okay. So I can pop out the 5 and make it look like this. So I'm multiplying, right? So order operations first, I add them up and then multiply, right? Because technically it's in parentheses, you want to call it like that. So you take the sum of this first and then you just multiply by 5. That's what that represents here. Okay. And then for number 2 is, what it says is you can literally break up the sum of any part. So anything you see addition or subtraction, you can basically distribute the sum in and take the sum individually and then add subtract at the very end when it comes to it. So you can think of it like this. So since I have that, I can now break them up. Individually. And then to get that sum first, then that sum, and then add them at the very end to get the whole thing. So we have to do it to every single step. Okay. Now, because of this stuff, we have some formulas when it comes to that. That's the best part. So if I want to find the sum of a constant number, okay, just a constant number, this sum is end up being c times whatever we end at. Okay. So here's an example down here, what I mean by that, of number 1. So if we want to find the sum of, let's say, a 30, so n equals 1 of just the constant 5, right? C is a constant. Okay. So what this is saying is if I plug in n equals 1, that's 5. N equals 2 is 5, right? It's just a 5, 5, 5, 5, 5, 5. And we're adding this. So 5 plus 5 plus 5 plus 5, 30 times. So the equation is I can just multiply them and get the answer. So this is the same thing as 5 times 30. It gives us a sum of the whole thing if I literally want to do it individually and then add them all up together. So that's going to give you, what is it, 1,500? Oh, 150 as the sum. Okay, so that's what that means. Number 2 says if I want to find the sum of k, so kind of like the sum of n. So that's 1, 2, 3, right? I'm just plugging in. That sum is equal to that there. Okay, it's a shortcut. Okay. And k squared and k cubed. So these are the 4 major ones we're going to be dealing with in on this section. And once you guys go into calculus, you'll get a little bit more detail. I think you're going to learn 2 more in the second part of calculus, but essentially these are the main 4 you always see in calculus classes. Okay, so basically what we're going to do now is we're going to use these to help ourselves out. We're going to use these portions to find the sums of new stuff